All right, so we are starting Unit 5, which is all about reaction rates, equilibrium, so things that we will define as we go. So today our focus is going to be on reaction rate diagrams and how to interpret them. This is going to tie us back into something we've talked about before, collision theory. We're eventually going to talk about how reactions require a collision, and based on these reaction rate diagrams, you should be able to tell things like, is this reaction exothermic or endothermic? And there'll be some vocab that we introduce you to related to these things. So first off, just kind of a general, you should already have an intuition on this, but when a reaction happens, what's going to happen to the concentration of your reactants? Should that go up or down? Now, as long as you remember that reactants are what you put into the reaction, what you start with, the concentration of your reactants are going to decrease as the reaction occurs. All right, and therefore what you produce or make in the reaction, your products, their concentration is going to increase. All right, so that's just kind of basic definition of a reaction. You're going to use up your reactants to make products. So reactants decrease, concentration of products increase. Collision theory comes back again, all right? So we've talked about this before. Hopefully you're kind of remembering maybe that Unit 2 lab or the whole idea behind dissolving. All right, so to dissolve salt into water, the water and the salt have to collide. All right. Same sort of thing is going to happen here. Whatever your reactants are, they need to collide. That way, bonds can be broken and new bonds can be formed in order to get that reaction to take place. So, some terms that you want to be familiar with. All right, we already kind of know reactants and products, but some new ones that you definitely want to get written down are going to be this idea of activation energy and a transition state. All right, so collision theory relates to reactions because that collision has to happen with a certain amount of energy to it. All right, think of it like, in, say, bumper cars, cars hit each other, but they don't get broken or anything like that. So those are light collisions, which is why it's safe for you to do as a kid in a ride. Whereas a car crash, which is a collision between cars, has a lot more energy to it. And when that happens, the cars break, they crumple, everything falls apart. All right, so kind of think of a reaction as like, all right, you need to have enough energy in this collision to actually get things to break apart. All right, and that energy, that minimum amount of energy that is required for, the bonds to break and everything to start shatter and fall apart, that's called the activation energy. All right, and when this happens, when, say you have two reactants, when they combine together, when they crash, and sometimes they even get stuck together temporarily, they make what is called this transition state chemical that is temporary, but it's necessary for the reaction to take place. All right, it's something that just, momentarily, like if you have two reactants, all right, they temporarily completely mesh together and then reform into whatever the products are supposed to be, which might be two different things. All right, so a reaction rate diagram is just kind of a visual of what's going on here in these words. So let's look at it. All right, so here's a reaction rate diagram. We've got our reactants. All right, so these are the chemicals that we're starting with. They have a certain amount of energy in them. And then we apply this E-act, which is your activation energy. All right, when we apply this activation energy, we make these two chemicals collide with a certain amount of energy so that we can push them into this transition state where you can see you've got your two chemicals, they're actually stuck to each other, they've collided. All right, and then some energy is released and these chemicals reform as the products. All right, so Couple of key things on these diagrams. All right, and these are things you're going to want to draw yourself an example. All right, enthalpy, this comes from Unit 4, that delta H, or you can also think of it as Q. All right, it's the heat that is either absorbed or given off by the reaction. All right, we've got our activation energy, which is always going to be above the enthalpy. All right, so that's essentially the difference between your reactants and the transition state. And then the enthalpy is going to be the difference between your reactants and your products. So if you kind of look at this reaction here, we've got our reactants starting out with this level of energy. Actually, I'm going to put this in blue. So we start out here, all right? Activation energy is always going to be higher than your starting point. There's always going to have to be a little bit of energy that is put into a reaction. But if you notice, our final energy is much lower than our initial energy. So energy overall in this reaction, if you think about from the start to the end, energy is released. So what could you say about this reaction? What's a term you could add? All right, this is exothermic. And I'm going to get cut off. Oh, no, okay. All right. So these reaction rate diagrams, we will work with these a little bit more, but this is something you've got to be able to kind of wrap your head around and interpret one of these. All right, so here's another example. All right, so you can tell that your reactants, right, they start down here, so I'm going to put S in for our starting point. All right, we're going to put in our activation energy. This one has a huge amount of activation energy. We got to get up to that transition state. That's always going to be the highest point on here. And then after the transition state, we drop down a little bit, but not as far as our starting point. So in this case, overall, from start to end, the energy increases. So energy is absorbed. All right. So like it says right here, that means we've got an endothermic reaction. All right, so this is just some key important things you want to be able to read and or label on these reaction rate diagrams, is know that, you know, reactants are always going to be your starting point, transition state is always going to be your highest point, products are always going to be your ending point. All right. The activation energy, so E-act, is your reactants to the transition state. All right, delta H, all right, your heat is always going to be reactants to products, whatever the difference is there. All right, and then you can tell if it's exothermic if your reactants started out higher than your products. All right, which means energy is released when the products are formed because there's less energy in the chemicals. And then you can tell it's endothermic if your reactants start out lower energy than your products, because that means energy had to go in or be absorbed to create the products. All right. So, real quick review here on those two terms. When a reaction is exothermic, the energy of the products, think about it here, we want to give off that energy, so we need to lose energy when it's exothermic, so the energy of the products is going to be less or lower than the energy of the reactants. Whereas when it's endothermic, it's going to be more or higher than the energy of the reactants. All right? So a way you can kind of visualize this is a good thing for you to be able to do, is see if you can on your own draw what this would look like. All right, so in a reaction rate diagram for something that's exothermic, the energy of the products is going to be lower than the energy of our reactants, so we can think of it this way, and just remember there's always going to be that hump for the activation energy in between these. All right. Endothermic, it's the other way around. Your reactants are lower than your products, but there's still always going to be that higher hump for that the E act. The hump is the E activation energy. All right. And then the difference between reactants and products, R and P, is the delta H. All right, so if you have questions about this, let me know. But definitely just being able to interpret a diagram, label reactants, products, transition state, activation energy, enthalpy. Those are the key components to this.